This is chapter 13 from Master Math Mentor's AP Calculus AB manual. It talks about the derivatives of inverse functions. Probably not a hard chapter to understand, but definitely a complex chapter. And this idea of inverses is kind of confusing. So let's talk about that idea first, and then we will get into chapter 13. So if we had a function, let's say our function was f of x, it's going to take some a value and give some b value. The a value being the input, the b value being the output. If we were to look at the inverse of that, we abbreviate the inverse with this -1, not to be confused with the reciprocal. What it's going to do, it's going to switch the input and the output. So the inputs and outputs are switched here. So if we can keep that idea straight, we should be okay with chapter 13. But at some point, it does get kind of confusing because it's going to say like, for the inverse, it's going to give you something like x equals 3. But what does that really mean? That really means on the original function that y would equal 3. So what we're really looking at here is this idea of something comma 3 for the original function. And then for the inverse, that would be 3 comma something. So we would need the x value for the original function, which is the y value for the inverse function. So if we could just keep this idea straight, that the inverse has BA, where the x value, x equals 3, is actually the y value for the original function. So suppose we were asked to find the derivative of y equals x squared at the point 2, 4. And we want to show that that is the reciprocal of the derivative of the inverse to y equals x squared at the point 4, 2. If you need a review of inverses, you can watch chapter 13 from Stu Shorts. His video does a really good job going over inverses in a lot more detail than I have. All right, so the function here, we're going to find the derivative of x squared, and derivative of x squared is 2x. And f prime of 2, the derivative at x equals 2, would be 2 times 2, which would be 4. And what we're showing here, what we want to show here is that derivative of the inverse would be the reciprocal of this. So the reciprocal of 4 would be 1/4. So that's what we're trying to do. We're trying to show that the derivative of the inverse is equal to the reciprocal of the original function. So here we got square root of x, which is x to the 1/2. Derivative of that would be 1/2 x to the -1/2 power, which is 1/2 times the square root of x. We move the -1/2 to the denominator, make it positive, and switch it back to a square root. We're going to plug 4 into that. We get 1/2 times the square root of 4. The square root of 4 is 2, and 2 times 2 is 4. So we do get 1/4. So we have shown that we have done this part right here. We have shown derivative of x squared is the reciprocal of the derivative of the inverse to that. All right, so for definition, if y equals f of x passes through the point AB, and f prime of x, or not f prime of x, the inverse of f of x passes through BA, then the derivative of the inverse at x equals b. Again, we got to keep this straight. This is this idea of a comma b, or b comma a, like which one are we looking at? For the inverse, we're looking at BA, and for the original function, we're looking at AB. This is equal to 1/1 f prime of x. But here we're taking this at x equals a. 1/f prime of x at x equals a. This can be stated more compactly. The notation here, I'm not fond of this notation, but the derivative of the inverse at the point BA, notice B came first, is equal to 1/the derivative of the original function at the point AB. So this would be the inverse function, and this dy dx would be the original function. Another way to say that would be to say that f inverse of x prime, so the derivative of the inverse function, is equal to 1 over f prime of f inverse of x. What this f inverse of x is going to do, it's going to take our b value, it's going to input x equals b, and it's going to give us a is going to yield this value of a back out. So we could rewrite this as 1 over f prime of a, x equals a, which is very similar to the definition that we wrote right here, 1 over f prime of x at x equals a. Rather than memorize this formula, we could memorize it. I would recommend you to memorize it. We're going to go over how to do this a couple ways, and you can pick which way you like the best. So the first way is to actually find the inverse. We're going to switch x and y, and then solve for y if possible. If we can't solve for y, then we're going to have to use an implicit differentiation. So let's look at example 2. All right, y equals f of x equals the square root of x plus 5. And we're asked to find f inverse of 3. This would be that point BA, the point BA. So back over here, this point would be 3 comma A. We don't know what A is yet. We might need to find that later. But then over here for f of x, this would be 3 comma B. So we just need to figure out what that A value is in this case. All right, so we're going to actually find the inverse. We find the inverse by switching x and y. So x is equal to the square root of y plus 5. And if possible, we're going to get y by itself. And in this case, that is possible. We can square both sides. So we get x squared is equal to y plus 5. And then we can subtract 5 from both sides. So we get y is equal to x squared minus 5. And we can take the derivative of that. So y prime, this is the inverse. So this y, this is the inverse function here. So the derivative would be equal to 2x. And we want to find that derivative at x equals 3. So since we are using the inverse now, x equals 3 goes right there. So y prime would be equal to 2 times 3, which is 6. So if we can solve for x, that problem is fairly easy. But suppose if we switch the x and y, solving for y is oftentimes really difficult, or sometimes even impossible. So we can't actually use the method that we used. So we're actually going to do some implicit differentiation here. So example 3, suppose we wish to find the derivative of y equals x to the third plus 3, y equals x to the third plus 3, if we were to plus x, sorry. And if we were to switch these x's and y's around, we would get x equals y to the third plus y. And solving for y in that equation is all but impossible. If we want to rearrange this in y equals and only x's on this side of the equal sign, that's going to be really difficult in this case. So that brings us to method 2. And I'm eventually going to show you a third method that's not covered in the book here. So we're going to switch the x and y's. So x equals y to the third plus y. But instead of solving for y, we're just going to go ahead and take the derivative using implicit differentiation in this case. The derivative of x is equal to 1. The derivative of y to the third is 3y squared dy dx. And the derivative of y is 1 dy dx. We can factor the dy dx out on this right-hand side, we're left with a 3y squared plus 1. That's equal to 1. And then we can divide by 3y squared plus 1. So we get dy dx is equal to 1 over 3y squared plus 1. Now, here's the problem. We want to find the derivative at, if we go back up here to the problem, it says that x equals 10. Derivative of the inverse at x equals 10. So this is actually for the original function for f of x. This is actually the point a, comma, 10. So this is actually the b value for the original, or the y value. So if we go back down here, how could we go about solving this? We can do one of two things. We can look at this and we can plug 10 into that equation for x, because that's the x value they gave us for the inverse, or we can plug 10 into this equation for y, because that's the y value that they actually gave us for the original function. It doesn't really matter which one we do, we're going to end up with the same answer. So just to stick to what the book does and how the answer key does it, they actually use this one. The x value they gave us was 10, and that's equal to y to the third plus y. Sometimes we can't really solve equations, but we can just without a calculator. But in this case, we can solve it by inspection. So if we were to just look and say, well, if y equals 0, well, that's not going to work because you get 0. What if y equals 1? If y equals 1, you get 1 to the third plus 1, which is 2. So that doesn't work. So let's try y equals 2. 2 to the third is 8, and 8 plus 2 actually works. So 2 to the third plus 2 actually is equal to 10. So y equals 2 would be our solution. So now to find the derivative at x equals 10, we actually plug in 2 into that equation. So that would look something like this. 1 over 3 times 2 squared plus 1, which would be 1 over 12 plus 1, which is 1 over 13, will be our final answer. I'll show you another way to do this problem, which is going to be using this idea of the definition that they gave us earlier, that the derivative of the inverse is equal to the reciprocal, 1 over f prime of x at x equals a. Remember, they gave us x equals 10, which was our actually equal to b. So we would still need to solve the equation and figure out what a was. So the derivative of the inverse, so f inverse of x prime would be equal to 1 over this idea of the derivative of x to the third plus x would be 3x squared plus 1. But here's where we got to be really, really careful. I cannot put 10 right there where that x is, because this x is at x equals a. And this 10 that they gave me is actually x equals b, this idea of a comma b. So for the inverse, they did give me the x value for the inverse, but that's actually the y value for the original function. So what I need to do is I need to actually solve this equation and figure out what a is, the same way we just did a second ago. So we're actually going to set 10 equal to x to the third plus x. And we'll solve that by inspection again. We see that x equals 2 is the solution to that. So we will plug 2 in for x, and we get 1 over 3 times 2 squared plus 1, which again is 1 over 13. I tend to like that method a little bit better, but it does require me to remember this, and it does require me to know that that x value that they gave me is not actually the x value that we're going to plug into the equation. So you can do these any way you would like. You can do them the way I did the first problem with the implicit differentiation. I don't think I'm going to do these others that way because I find it more convenient to say that the inverse derivative is equal to 1 over f prime of x at x equals a. And f prime of x, the derivative of 2x to the third plus x squared minus 1, is 6x squared plus 2x plus 0. But in this case, at x equals 2, I can't plug 2 in because that's the b value. This is really x equals b. So we would have to set our equation 2 equal to 2x to the third plus x squared minus 1. And again, this chapter is not hard. It's just very confusing because why can't we just plug 2 in? Why do we have to solve this equation? Because this 2 goes with the inverse. This is the x value for the inverse, which if we're looking at this point a comma b, that's actually the y value for the original function. So the y value for the original function would be f of x or y. And then we can solve this by inspection as well. By looking at that, if we tried x equals 0, we would get 0 plus 0 minus 1, which is -1. That doesn't work. If we tried x equals 1, we would get 2 times 1 to the third plus 1 squared minus 1. The 1 squared and the minus 1 would cancel each other out. 2 times 1 to the third is in fact 2. So we see that that answer is x equals 1. So this is this derivative, 1 over this derivative at x equals 1. So we get 1 over 6 times 1 squared plus 2 times 1, which is 1 over 8 will be our final answer. We could do that a different way using the implicit differentiation that we did earlier, but I find this other method to be a little bit more better. All right, number 5, we're looking at the derivative of the inverse is going to be equal to 1 over f prime of x. This -3, x equals -3, is really x equals b. So again, we're going to have to figure out what is x equals a, because this formula we're using is at x equals a. So 1 over the derivative of e to the 4 minus x is e to the 4 minus x. We're going to use chain rule and multiply that by the derivative of 4 minus x, which is -1, minus the derivative of x is just 1. So we end up with 1 over negative e to the 4 minus x minus 1. So what value are we going to plug in for x? We can't plug in -3. We have to figure out what that value is. So we're going to set -3 equal to our equation, e to the 4 minus x minus x. And again, we can solve this by inspection. Sometimes we just want to look at it and see, just start trying some positive or negative numbers. If we try 0, we're going to get e to the 4, and that doesn't work. If we try 1, we get e to the third power minus 1, that doesn't work. If we try 2, we get e to the 4 minus 2, which is e squared minus 2, that doesn't work. If we try the third power, we get e to the 4 minus 3, which is e to the first minus 3, which is not -3. But if we try x equals 4, we get e to the 4 minus 4 minus 4. E to the 4 minus 4 is e to the 0 minus 4. E to the 0 is 1, and 1 minus 4 is -3. So the number that we're actually going to plug in, x equals a, would be x equals 4. So we're going to plug 4 in, and we get 1 over negative e to the 4 minus 4 minus 1, which would be 1. Negative e to the 4 minus 4 would be negative e to the 0, which would be -1 minus 1. So we get 1 over -2 would be our final answer. That would be the slope of the tangent line of the inverse of f of x at x equals -3 on the inverse. Number 6, notice the calculator. We're going to use the calculator this time to solve an equation. So you're just going to have to listen very carefully on how to solve that equation. I might can try to show you. We'll see if my calculator and iPad will cooperate. So f inverse of x prime is equal to 1 over the derivative, which would be 3x squared minus 8x plus 7. But at this case, it's at x equals a. And this 1 is actually x equals b. It goes back to this idea at the beginning of the chapter that we talked about, where f of x takes a as the x value, b is the y value, but in the inverse actually switches those. So what they've given us at this point they've given me x equals 1, which would actually be here and here. In order to do this, I need to know what that is. So what is the x value when y equals 1 on the original function? And solving for that this time by hand is impossible. Doing it by inspection is also impossible. So I'm going to try my best to show you this on the calculator.
All right, on the calculator, we can basically solve any equation we would like by using the graphing technique, where we graph the left side of the equation, the right side of the equation, and then we calculate their intersection point. So in y1, I've typed in our original function, x to the third minus 4x squared plus 7x minus 1. And in y2, I went ahead and typed in what we want that to equal. We want that to equal 1. So then we would hit graph. We want to make sure that we actually have the intersection point on our screen. As long as the intersection point is on the screen, this method will work. We could zoom in a little bit if we wanted to, just to make it look a little bit nicer. And we can zoom in around that intersection point. And as long as that intersection point is on our screen, we could actually calculate that. So how are we going to calculate that intersection point? See the blue calculate button right there? We're going to hit it. So second, calculate. And we want to calculate the intersection point. So we're going to go down to number 5. It's going to ask for the first curve. So it looks like my first curve. It looks like I'm on the blue curve at the moment. So I'm just going to hit enter. It doesn't matter which one's the first curve. And then where it says second curve, as long as I'm on the other graph, y1 or y2, as long as I'm on the other one, it's okay. It says guess. We could scroll over and get close to the point where it intersects if we wanted to. And we see that x equals 0.349.
Saw from the calculator that this x equals a was 0.349. So we can plug that back in. So we get 1 over 3 times 0.349 squared minus 8 times 0.349 plus 7. And you can type that in the calculator. They're not going to want you to do that without a calculator. And when you do type that in the calculator, we get an answer of approximately 0.219. And that would be our derivative at x equals 1 of the inverse function. Number 7, find the derivative of the inverse to f of x equals e to the x. So f inverse of x prime, the derivative of that would be 1 over derivative of e to the x is e to the x. Derivative of ln x is 1 over x at x equals 4. Remember, that's x equals b, and we want x equals a. So what you can do in y1, we can type our original function, e to the x plus ln x. And in y2, we're going to type in 4. And then you're going to hit the graph button. You're going to make sure that where the two graphs intersect actually show up on the graph. And then you're going to hit second, calculate. And you're going to go down to number 5, which is intersect. And you're going to calculate that intersection point. I'm not going to show that on the calculator this time, but that intersection point is 1.315. And then we would plug that 1.315 back in for x here and here. So we get 1 over e to the 1.315 plus 1 over 1.315. And when you type that in your calculator, we end up with 0.223. So the slope of the tangent line of the inverse to f of x equals e to the x plus ln x at x equals 4 for the inverse is 0.223. All right, number 8, the function f is differentiable for all real numbers. The table to the right gives values of the function and its derivatives at x equals -1 and x equals 4. If f inverse is the inverse function of f, find the equation of the tangent line to the graph at y equals f inverse of x at x equals 4. Remember, this is x equals b. So if we're looking at this point, a comma b, it's going to be a comma 4 if we're talking about f of x. And if we're talking about f inverse of x, it would actually be 4 comma whatever this value would be, because a and b would actually be switched. So this would actually be the a value of the original function. So if y is the inverse, then y prime would be equal to f inverse of x prime, which would equal 1 over f prime of x at x equals a. But we don't know what x equals a is. We don't know what x equals b is. But if we look right here, it says the y value is 4. What is the x value for that point? The x value would be -1. So if we go back up here, this a right here would actually be -1. So what we're actually looking at is 1 over f prime of -1. And f prime of -1 is -2. So we're looking at 1 over -2. So that would be the slope of the tangent line of the inverse at x equals 4. The equation would be y minus the y value. So what would the y value be? The y value would actually be, we got this 4a would be 4 -1. So this is our x1, y1, because we're using the inverse. So y1 would be y minus -1 is equal to the slope. The slope is -1/2 times x minus the x value, which is 4. And we could solve for y if we needed to in that case, but I'm fairly certain that all of you would be able to solve for y. So while this chapter is not hard, it could be very confusing because of this a4 and 4a piece, that the inverse and its function, the x and y values are switched. If you have any questions, please let me know, and have a good day.